All right. Hi. Welcome back. So today we're going to look at double integrals over more general regions. So let's start this. Okay. So the idea is that integrating over rectangles is not going to do the job for us. So we'd like to be able to integrate functions over domains which are not rectangles. So how are we going to do this? Then the trick is actually pretty simple to some extent. So here's the idea. Okay, so we want to integrate functions over regions more general than rectangles. Okay, so we're going to define the following, which is very simple. The notion of bounded region. Okay, so a region, which is just a subset S of the plane, we'll say that it's bounded if it's contained in some rectangle. So in other words, it doesn't fly off to infinity in any direction. Okay, so you can think of something like this. This is S. You can draw a rectangle around it. That means that the region is, we call that a bounded region. Okay, so we're going to integrate over regions which are bounded. It is possible to integrate over regions which are not bounded. And you've done something similar in Cal 2. These integrals of functions from, let's say, minus infinity to infinity. We're not going to do this here, except in one example that I want to do, but it will be simple. So here is how we're going to define this. It's very natural. Okay. So hopefully I can switch slides. So here we go. So let F be defined on some region S, where S is bounded. Okay. So we're going to define the double integral of F over S as follows. Okay. So the notation is what you would expect. Double integral over S of the function F. Okay. So how are we going to define this? Well, what we're going to do is just take any rectangle that contains S, like that, and integrate a slightly different function. Okay, so let me tell you what the rectangle and function are. So R is any rectangle containing S. Okay, and so it doesn't matter which rectangle you choose. Okay, and how do you define the new function big F? It's the natural way. So big F is going to be the same as little f over S. And outside of S, you don't want anything to happen, so you set it to 0. Okay? So I'm going to draw a picture of what this might look like. Okay? So here, sip of water. Okay, so it looks something like this. So I'm going to, again, assume my function is positive so it's easier to see. So this is x, this is y. I have a certain rectangle that contains my region S like that, okay? The function lil f has its graph over S, right? And on the rest of the rectangle, it's 0. So that's the situation. So that's how big F, so the whole thing here is the graph of big F over the whole rectangle R. So you're going to say, oh, wait, sir, that's awful. There's like this big jump. Yes, there's a big jump, okay? And this is the reason why in Fubini's theorem, I needed that thing that said, I can apply Fubini if my function is continuous over the whole rectangle, except maybe, let's say, on some curve, which is exactly the situation here, okay? So hopefully you see that the choice of the rectangle doesn't make any difference, right? So because the function is 0 outside the region S, it doesn't contribute to anything in the integral. Okay? So yeah, I should say this is S. Okay. So so that's the first comment. So clearly, choice of R, it doesn't matter. Right? And the second thing is just what I said is if lil f is continuous on S, then big F will be continuous on R, except on what we'll call the boundary of S. Okay. Now I haven't put any conditions on S right now, except that it's bounded, so it's contained in a rectangle. So it could be just really junk. But the examples that we're going to deal with, the region S will be nice, and the boundary will simply be a curve, and that has measure 0. Okay, so if S is decent, its boundary is a curve, so has measure 0, and so Fubini can be used. Okay, so it should be safe. It should work out okay for us. So now what I want to do is, first of all, and if you're looking at the book, this is actually maybe in older editions new it. I don't know. They've changed a few things, but the basic properties of the integral defined this way are given maybe at the end of the section. I want to do them now, and after that, I'll show you how we can use Fubini to actually compute integrals like this. Okay, so I'll first start by giving you some basic fundamental properties of the integral in general. Okay. So that's my next goal. Okay, so some basic properties of the double integral over bounded regions. This is S, okay? So I'm assuming here that everything is nice and exists, and we're not looking at anything nasty here. Okay? So okay, so I'm not going to rewrite the whole hypothesis here. So the first thing, which is what I'll call linearity, is what you would expect. And if you're doing linear right now, you may have seen linear transformations. And basically what this says is that the double integral over S is a linear transformation, but you don't need to know that. So here, what I mean by linearity, there are two properties. The first one says, and this will not surprise you, that if you take the double integral over S of the sum of two functions, then you can split it as the sum of the integrals. I'm not going to prove any of these properties here. You can always use them. Okay, so that's the first part of what I call the linearity property of the integral, so that the integral of a sum is the sum of the integrals. The second part is, and there's always these two things when we're talking about linearity, they behave well for sums and constant multiples, okay? So that's the second property, that the double integral of k times a function, you can factor out the constant. Okay, it has to be a constant, obviously. Okay, so that's our first property in two parts. So integral of a sum, sum of the integrals, integral of a constant multiple is the constant multiple of the integral. Okay, just like the integrals you saw in Cal 2. Okay, so now let's look at some other different kinds of properties, which all of them mimic or are the same that you saw in Cal 2 for the one variable case. Okay. So here's the second one. It says that the integral is order preserving. So what does that mean? It means that if you have two functions such that f is always less or equal to g on S, so when x, y is in S, then the same thing holds for the integral. And I hope that makes sense. It's natural. Right? Since this is a sine, oops, this is a sine volume, this should make sense, right? Like this. So if you take a function f, or you take a function g which is higher, then the integral of g will be bigger than the integral of f, right? Okay. The third one is what I call splitting. This is not an official term. It's just for me to remember it, okay? This is similar to a property you saw in Cal 2, which if you remember, if you have the integral from a to b and the integral from b to c, their sum is the same as the integral from a to c. This is similar, but way more general. And so here is the statement. Well, suppose that your region S is the union of two pieces. okay, which don't overlap, okay? So they might overlap, but only, let's say in a curve, in something of measure 0, okay, where their intersection has measure 0. Okay, so in other words, we don't overlap except maybe on a curve. Okay, this is to be taken with a grain of salt, but to give you the image, so you can split S into two pieces. They might have like a boundary, but they can't be one. They can't have a common part which has actually area. Okay, so you're not allowing this. But suppose that S splits up this way, then you can probably guess what the property is that the integral, the double integral over S of your function f will split as the sum of the integral of f over S1 plus integral of f over S2. Okay, maybe I can draw, let's say this is S, this is S1, S2, something like that. Hopefully that makes sense. I think you can probably believe that. Okay. Okay, so we've got three properties, just two more. The next one is a way to compute area. Now that looks very strange, to use something, to use a technique to measure volume, to use it to measure an area, but sometimes it actually is the only way that will work, and it's easier this way. It's strange, but that's how it goes. So here is what I want to say. So you have a region S. Okay, and it'll be bounded. My regions are always bounded. Okay, then I can compute the area of S as follows. I can take the double integral over S of what? Well, you have a flat area and you want to see this area as a volume. So if you take something of height 1, the volume will be 1 times the area of S, so that's how you can get the area. So you integrate the constant function 1 over S, and this will give you the area of S. So here's the idea. Let's say this is your region S. If you look at something of height 1 over it, right, then the volume is equal to area of S times 1, right? That's the idea. So it looks a bit weird to compute an area as the volume of something, but sometimes it's actually very useful. Okay? And one last property, which is something you also saw in Cal 2, which can be useful if for some reason the integral you're trying to compute is just really too difficult. You might want to approximate it. Then this is one very elementary, very rough approximation that you can get as follows. So suppose that you have bounds on your function f. So suppose that you have two values, little m and big M, such that f is always caught between little m and big M on S. Then you can you can have a rough estimate of your double integral as follows. So in fact, this 5 will follow from properties 3 and 4. So little m times the area of S will be less or equal to the double integral over S of F less or equal to big M times area of S. I don't know if I can try to picture this, but that's going to be tough. Okay, so this looks like a hamburger, but I don't know what it looks like. But anyway, so this is S. This length is little m. This length is big M, and this is the graph of your function f, right? So if you're looking at the integral over S of f, this volume is certainly bigger than the volume of the hockey puck at the bottom, which has volume area of S times little m, and it's less than the soup can, right, which has volume big M times area of S. Hopefully this makes sense. Does that work? It's not something that you're going to use like that many times, but there might be a couple of exercises where you have to estimate what's going on, and this could be useful. So note, this follows from its properties 2 and 4. It's a combination of both. Okay, so just you combine 2 and 4 to get this one. Okay. Any questions up to this point, or is this? Okay, sorry again, I can't see thumbs up if there are any, or thumbs down. I don't want to see those. Okay, we got a little chat here. I always enjoy those. It's all good. Excellent. Very good. Yes. Okay, so back to how can we actually use this to compute things. Okay, so okay, so let me refresh your memory about something you saw in Cal 2, which are regions of type 1 and type 2. Okay, so what is that? So a region is of type 1 if basically it's everything in between the graphs of two functions, right? Between over some interval. That's what type 1 is. Okay, so a region S is of type 1 if S is equal to, so it's all pairs XY such that X is between A and B. I'll tell you what these are. And Y is between G1 of X and G2 of X. Like this, where A is less than B and G1, G2 are, and we'll say they're continuous on AB, and G1 of X less or equal, and there's a lot of stuff, but it's actually very simple. What is the word after a region? the one you wanted, yes? All right. Okay, so a picture is worth 1,000 words. So what does this mean? What it means is you have these two numbers a and b. You have the graph of a function g1. You have the graph of a function g2. And s is everything here. This is s. Okay? You remember those for sure. Okay? So I have two functions, one on top of another, and I look at all the points which have their y-coordinate between the graphs and their x-coordinates between a and b. Now, often it's not going to look exactly like this. It's possible that G1 and G2 intersect. That's a very common. Might also look like this. Right? It's possible that they meet actually like that, right? Or also they could intersect at both ends, right? Like this, right? So something like this, okay? Now, if you have a region of type 1, which is what you're hoping for when you have a double integral over a region, if it is, does an intersection have to correspond to an extremity? Good question. Actually, in our context, okay, the answer is no. So the following could happen. So this might happen. In theory, you might have something like this. Let's say something like that. This could be your region. Yeah, so you're right. It could look like that. But if that's the case, actually, no, sorry, that cannot happen. Because G1 has to be less than G2 over the whole thing. I mean, you could have a region like that, but it's not type 1. So I'm sorry. This is, I mean, G1 would have to be the top curve, and it'll be defined by some nasty piecewise thing. So yeah, theoretically, this is possible, but I don't expect you to see this. Okay, so no, let's not. We'd have to split this up into pieces. Okay, so actually no. Yeah. So forget what I just said. I mean, theoretically, this could happen, but then the functions G1 and G2 would be very, very messy. Okay, but once I do examples, you'll see pretty much what you're going to see. It's not. It's. I need the description right now to show you how to compute in general, and then we'll do examples, and you'll see it's not so bad. Okay, hopefully that's sort of clear. I'm sorry. Okay, so here's our theorem. So now we can integrate over regions of type 1. Okay, so if f is continuous on S of type 1, Okay, let's say S is, and I need names for the whole thing. Okay, then we can compute the double integral of f over s as follows. And this is new, okay? So this, what I'm going to write is something we haven't seen before. So this is the integral from a to b, integral from g1 of x to g2 of x, f of xy, dy, dx. So the thing you notice clearly are those limits of integration which are not constant. They are values of the function, right? So that's what's new here. So this is not really difficult to see why it's true. I'm going to show you, okay? So this is the proof, or the idea, it's the same thing, okay? And then I'm going to do an example. What time is it? Okay, so I'm going to show you the idea of this and do an example, and that'll be it for today. Okay. So how does this work? Okay. So again, recall that the double integral over S of lil f, what is that? By definition, this is the double integral over some rectangle that we choose that contains S of this new function, big F, which is little f on S and 0 outside. Okay? Okay, so here's the picture. So again, F is little f on S and 0 otherwise. Okay, and the rectangle. So here's a picture of what this will look like. So I have a rectangle, and again I can choose the one that I want. So this one I'm going to choose from A to B. That's the simplest. Okay, and I have my two curves, the graphs of G1 and G2 like that, right? And the region S is what's over here. Okay, and this is my rectangle R like that. Okay. So these curves are the boundary of S. They have measure 0. So Fubini actually applies. Okay, so Fubini applies here. The curves, they have measure 0. Okay, so we're good. So you have to see the function that lives over this with some function over S, but it's 0 on those two little pieces here and here, right? So the function is completely flat. Big F is completely flat there. Okay. So anyway, let's apply Fubini. So the double integral over S of little f, right? This is defined as the double integral over the rectangle R of big F, the stranger looking function. I'm applying Fubini here. So I'm going to get the integral from A to B. So sorry, I should have added in my picture, this is C. And this is D. Okay, so I added something to the picture. So this is the integral a to b, c to d of big F. E, y, d, x. I am choosing that particular order to do it. You can't do it in the other order, okay? So I applied for B equal. Now the problem now is, so again, we want to do an iterated integral. What is F? It's not in, so the question is in the drawing, what is F? You don't see it, I'm just looking at the domain. F is living over, over this, right? The graph of F is over here. Is that, I don't know if that helped. Do you see what I mean? Okay. So I'm just looking here in the xy plane is the domain, and the function little f is over the region S. And big F is the same as little f, except it's 0 on the two starred pieces there. Okay. Okay, so now I have this iterated integral. So we should be happy, right? We're gonna just do one variable integrals, but then you look at that function big F and say, wait a minute, this is a weird function. It's like, it's 0 on both ends, and in the middle it's not 0. So how do I find an antiderivative for that? So that's the last step that we want to do, okay? So we're going to take a look at what happens here. So we modify to get a nicer integral, okay? So now what I'm going to do is, so you remember how this works. So your inside integral, x is constant, right? So we're going to fix x and look at that inside integral. Okay, so you fix x and consider this inside integral. Integral c to d of big F xy dy. Okay, so that's what I'm looking at. So maybe I should redraw this. X, y. So x, I'm going to fix a value of x like that. I have my rectangle like this. I have my curve G1. I have my curve G2. Okay, I fix the x, and I'm integrating the function big F from C to D. This is C to D, right? So from here to here, what does the function look like? Well, over the interval here, it might look like that, but here it's flat. Okay, I'm just going to draw that slice. Okay, so the slice at x, right? So now our variable is y, like this. We're going from C to D, okay? Now, the function big F is 0 over here, and it's little f over here. That's the graph of big F, right? So this is graph of big F when x is fixed, right? So it's 0 outside S, and it is equal to little f of xy inside. Okay? So now I want to take the integral of that function between C and D. But what is that? We can split the integral into 3 pieces, and 2 of those pieces are 0, right? So we can just get rid of those. So we just have to remember what are the values which are here. So look, go back to the picture in 3 dimensions, right? So this point is on the graph of G1 and the other point is on the graph of G2. So this is G1 of X for that fixed X, and this is G2 of X right here. Okay, so clearly the integral from, from C to D of big F, this is equal to, I'm going to split it up into 3 parts. Integral from C to G1 of X of big F plus integral from G1 of X to G2 of X of big F plus the integral from G2 of X to D of big F. Everybody's okay with that? It's just typical thing you did in Cal 2, right? You have an interval, you have the integral from one end to the other. You can split it up along points on that interval. Okay? Okay, so I'm going to recopy this on my next slide. There. Okay. And so now, so what happens? So here, what is that integral? It's a big fat 0, right? Because big F is 0, and this is 0. This is also 0. Right? And over here, what is big F is the same as little f. So this is the graph of little f. So this thing is equal to the integral g1 of x to g2 of x of little f. Right. Okay? So you take an x, you slice that x, and you just look at that integral. You want to get rid of that function big F because it's sort of piecewise defined and nasty looking. And you can. What's the cost? The cost is you don't have those constant bounds for all the slices. The bounds will change depending on the slice that you're using. Okay? But it's a very small cost. Okay? So if you look at what I just did, if you go from here to here, it gives you what we wanted. Okay? So what I want to do now, unless there are questions on what I've just done, hopefully, I mean, this is sort of like semi-heavy, right? It's theoretical, but I think each little piece is not too bad. But from a computation point of view, I'm sure that you'll be fine, okay? So does that look okay for now? Yeah. Everybody's gone to sleep. Everybody's gone. So good. All right. Excellent. Okay. So let's do an example. Okay. Here it is. What time is it? Okay. So we're asked to find the volume of the solid which that lies between below the paraboloid z equals to x squared plus y squared and above the region S in the xy plane, which is bounded by the following curve. The line y equals 2x and the parabola y equals to x squared. Now, if you take a step back and you look at that problem, I mean, that's a pretty nasty solid. I mean, it's just like not super obvious, right? But now we have the tools to actually compute the volume of this complicated solid. Okay? So I'm not going to attempt to draw this solid. It's hard to do, okay? But what's important in all these problems, of course, is, okay, you think I have to set this up as an integral, right? So set up as a double integral. So what do we need? I need a function f to integrate and a region S. Although if you look at this problem, it's pretty clear what these will be, okay? The other thing is, once you have your region S, to use what we've just done, you need to see that it's a type 1 region. We'll see other types later, but for now, that's the only tool we have, okay? And express S as type 1. That's for now. We'll see other possibilities later, but mostly that's it. Right? Okay, so it seems reasonable here. So it's sort of clear here. Since the solid is everything below the paraboloid, that the function f that we'll be integrating, then its graph is z equals to x squared plus y squared. So that will be our function. And s is given. Okay, so our volume will be the double integral over s of x squared plus y squared. Okay, so that's what we're trying to compute. To compute that, if I can manage to express S as a type 1 region, I can use the last result, and it should be fine. Okay, so need to express S in type 1. Okay? And in most of these problems, and we're not even going to go that far, but even double, triple integrals, the meat of these problems is always the region. You have to manage the region, and once you've done that, then you integrate. But that's usually the thing you have to figure out. Okay, so what is this region we're given? It's actually something, I think this is even in a problem from Calc 2 where you have to actually find the area of this region. Okay, so this is S. So let's take a look in the plane, what it looks like. So I've got y equals to x squared, and I've got y equals to 2x, which looks something like that, right? So that's S right there. Is it type 1? It looks type 1, right? So how do you check if something is type 1? Look at vertical slices. Are the bottom and top points lying on the graphs of two functions? Yes, right? So it's type 1, clearly. So now I just have to write down what A, B, G1, G2 are, okay? So here you see that you're not given A and B, How do you find them? You remember that? You find the intersection points, right? Okay, so this one is not too hard. X squared equals to 2x. X squared minus 2x is 0. X times x minus 2 is 0. 0 and 2. Right? So we've got our A and B. So A is 0, B is 2. G1 is the small function, which is x squared. G2 is the big function, it is 2x. Right? So let me write S. S is the set of all xy such that x is between 0 and 2, and y is between x squared and 2x. This is S. Okay? So, the last theorem says that the double integral over S of whatever, it makes no difference, but here we have x squared plus y squared. This is equal to what? So now, okay, so this is like super important. The constant bounds are outside. It makes no sense to have non-constant bounds on the outside. You won't get a number, okay? It makes absolutely no sense to have that. So this is the integral from 0 to 2. These are A and B. Integral x squared to 2x of x squared plus y squared dy dx. Okay? So I've set up my integral using the last result because my region is type 1. And now I need to compute. Okay? So far, so good. There's a lot of stuff flying around, but how do you know which function G1 and G2? Yeah. In principle, I should check, but here the functions are so simple that I could just simply draw them. The point is here is that usually you'll get pretty simple functions, but okay, maybe that's not your question. Okay, so let me just go over here and paste that. That's what I want to compute. Yeah, I have a line and a parabola like that. Okay, so choose an x, any x between A and B, and look at the segment inside S. Here, look at the bottom point. What is it? This is x squared, right? Look at the top point. This is 2x. For any x that you take between the two intersections, the bottom point is x squared, the top point is 2x. So it means that the points on the segment here, these are points xy such that y is between x squared and 2x. Does that make sense? All right. Okay, so that's how I know which one is G1 and G2. Okay, so now I want to compute this. Okay, so that is here. Now we compute this. So it's an iterated integral. So what do? You start on the inside. You cannot in this context, it is impossible to flip. You have non-constant bounds. They must be inside. There is no way to flip things around, okay? This is crucial. Okay, so inside integral, x is constant, right? I integrate with respect to y, so this is x squared y plus y cubed over 3 between x squared and 2x, right? So what is that? Then I just replace and subtract. Again, the outside parts, the integral 0 to 2 and the dx are just there for the right. I'm not doing anything with those right now. So now I replace, so this would be x squared times 2x plus 2x cubed over 3 minus x squared times x squared plus x squared cubed over 3. Right? So I'm just evaluating the usual way. Okay. Now, of course, I could simplify what I have here. I'll play a little bit with it to make my life easier. Okay. Paste it here. Okay. So this is integral 0 to 2. So this is 2x cubed plus 8x cubed over 3 minus x power 4 minus x power 6 over 3 dx. Nice polynomial, easy to integrate. Right, you're not supposed to have any y's left, right? You've integrated with respect to y, use the fundamental theorem, you replace, and so you get 2x power 4 over 4 plus 8x power 4 over 12 minus x power 5 over 5 minus x power 7 over 21 between 0 and 2. And you evaluate this. 8 times 2 power 4 over 12 minus 32 over 5 minus whatever, 128. And you compute that and you will find 216 over 35. Right? Now, suppose you're doing a problem like that and you get a negative. What do you think? You think, I messed up, right? If you look at what you're given here, it's a volume. You're supposed to get something positive. There's nothing negative in this setup. So the paraboloid is all over the xy plane. You're integrating over a region. You're supposed to get something positive. That's just a little observation. Okay. So, any questions? This is it for today. There's one last thing that I want to say, but if there are questions first on this example or anything I've done up to now. No questions? Somebody left. Okay. What I want to say is I would like to do a quiz next week. The reason is that it would be a dress rehearsal for our test, right? So, so next week we'll have a quiz where I'm going to send you out the questionnaire, you answer, submit it back through Leia using a scanner and I'll tell you the best ways to do it, okay? So this way, it'll be a practice for what's going to happen with the test. Okay, so it's going to be a short quiz, but you'll have enough time to do it and to scan. What sections would be included? That's a good question. Let's say, yeah, the quiz is just like the regular quizzes, right? So it's not worth that much because there are many quizzes and web works, so it's like a little, but yes, it'll be worth something. I'll think about what it should be on. Probably 15.1, 15.2. Or maybe I could add this. I don't know. But integration, not chapter 14. No, chapter 15 up to some point. Probably 15.1, 15.2. Okay, so integration over rectangles. All right. Questions? Is it possible that we do the test on the 14th of May instead of the 13th? Is the final exam cumulative? No, it'll be the test. It's a test. Okay, I'm just getting like tons of questions all at the same time. Okay, wait, one thing after another. For the quiz, yeah, Thursday would be good for the quiz. Is the final exam cumulative? No, it will not cover what was covered in the last test. So it'll be chapter 14, 15, what's left. And the other question is it possible that we do the test on the 14th of May instead of the 13th? So I have a problem. The problem is I can't do the test in a class which is not 2 hours. It's just not possible because you need enough time to do it and you need enough time to scan it. And I cannot overlap with other classes. I can only do tests during a period, which is mine. And the 13th is the last 2-hour class that we have. Will we be allowed to have more than 2 hours to do the test, to scan and submit? I think you're okay if the test is something like 80 minutes. If you have 2 hours, I think you're okay, right? So with 2 hours, you should be okay to do the test and scan. Yeah, that'd be fine. Yeah, the test is not going to be 2 hours, right? So the test will be roughly an hour and a half. So that means you have at least a half hour to scan or whatever you need to do to send it to me. Yeah, the test will be a PDF that I send out. Yes. And you'll have to submit it through. That's why I want to do a quiz so that you'll see the process. Yeah. You can do it on an iPad. You can do it on anything you want, as long as what I get is submitted through Leia and it's a PDF, then I have no problem. You can do it. Do I have a practice test? I probably have something around, yes, that I can try to cook something up and send it to you for sure. Yeah. Other questions? When are we going to finish the content? That's a good question. It's really hard to gauge. If the test is on the 13th, that means we have like the rest of this week, next week, and after that, that's it. So I'm hoping that next week I'm done, which means that I'm not going to be able to cover everything I wanted to. But that's the way it is. That's the way it is. I'm almost going to cover everything, I think. Yeah, I think so. When is web work number 3? Yeah, I should. I have to. I have to get it out there right now. It's coming. Yeah, absolutely. Can have a class on the practice test. Yeah, so that's what. Yeah, that's a good idea. So what I could do is send it out, and maybe the Monday 11th, then we could work on that. Does that sound okay? All right. Yeah. And for those of you who are with student services, you have extra time, we need to fix that, right? So we need to tell me as soon as possible if you're using extra time for this. And I have to contact people at the college to see how this works. Okay? Yeah. Anything else? Okay. So it's all good. All right. Okay. So I'll see you tomorrow, I guess. All right. Cheers. Bye bye.